Okay, last section, 6.4 probability. I have tried to fill out some of the notes in hopes to keep these notes shorter. We will see. So probability, we first have to talk about a sample space. So sample space is all the outcomes that are possible. So if I toss a coin, my possibilities are heads and then tails, and that's it. Yes, it could be tails and then heads, but we're saying that they're that it could be, those are our options because it's only one coin toss, so it can either be heads or tails. However, if two coins are tossed, we could have head, tails, tails, heads and then tails, or tails and then heads. So there's 4 outcomes for my sample space. If 3 coins were tossed, notice I have 8 coins in my sample space. So when we are finding probability, it's the number of events, so whatever we're looking for, divided by the number in the sample space, okay? So if we go back and look at what I did, the 2 coins tossed here, what's the probability that they both land on heads? Well, that's 1 out of 4, because if I look at my outcomes there's only one of them of 4 that could be heads. And of course, also recall some of your decimal fraction skills. So 1 divided by 4 is 0.025. To find the percent of that, you multiply by 100, so it's 25%. I won't be converting all of them every single time, but just a reminder that that's what it could be. I did the next one for you. Here's what your 52 cards could look like. I made sure to give you that picture in case you're not familiar with a deck of cards these days. And it says, what's the probability of an ace? Well, 4 out of those 52 could be an ace, which is 1/13. Again, you could change that to fraction and decimal if you wish. Next, we have 2 6-sided dice, and we're going to roll them, and we want to know the probability that the 2 die add up to 7. So first we need to know how many total outcomes there are. So we're going to use that fundamental counting principle from last set of notes here. I have 6 outcomes for the first roll. I have 6 outcomes for the second roll, for a total of 36 possible outcomes. Okay, so how could I get 7? Well, I could get 1 and 6, 2 and 5, 3 and 4, 4 and 3, 5 and 2, 6 and 1. Those are all the possible ways that I would have the number 7. So that would be 6 out of 36, which is 1/6. So hopefully a lot of this part of the probability is review for you. If not, that's okay, but we did do a little bit in Algebra 2 last year. Okay. What if we use some of that permutation and combination stuff that we learned last class for probability? So back to the lottery. Okay. Another reason your math teacher would never advise playing the lottery. Let's say that we wanted to choose 6 different numbers from 1 to 40. If these 6 match, again, order does not matter, the winner or the player wins or has to share, because it's possible more than one person pick those 6 numbers, the top prize. What is the probability of winning the top prize? So I kind of gave you a hint there. Order does not matter. We're just choosing the 6 numbers, not which one got drawn first, second, third, so forth. So since order does not matter, that's going to be combination. So out of the 40 numbers, we are going to choose 6 of them. To save time, I'm not switching over to Desmos. However, maybe you should. Make sure that you can get 3,838,380 different ways. Now that's not a probability. Remember, your probability is a fraction. There's only one order number that wins out of almost 4 million different ways. And this is why the lottery exists, because not very many people play, but they think that they might win. but the state keeps doing it because they still get money. They're winning. So really, they're the winners here. Okay, next term, mutually exclusive. This was an Algebra 2 concept, but I will talk about it again. Mutually exclusive is when they have nothing in common, but sometimes they do. So the formula here is probability of event A plus probability of event B minus probability of A and B. I call that the overlap, so you'll notice I put that word overlap there. If they're mutually exclusive, so nothing in common, then I would just add them. Probability of A plus probability of B. Okay? So in this example, we're looking at 52 cards again. What's the probability that the card is either a heart or a face card? So if you're looking at all of them, you don't even have to use a formula. We could do a heart, here's all my hearts, or a face card. So I just count those up out of 52. And get 22 out of 52. To me, that's the easiest way to do it. Okay, which is 11 out of 26. To use the formula, I would do, let's change our color here. The probability of event A, so that's 13 out of 52, is a heart. The probability of event B, which is a face card, if I count those all together, so that is 12. But notice that these three right here got counted twice. They got counted in the face card and they got counted in the heart category. So we have to take away that overlap because they can't be counted twice. They only need to be counted once. So that's 25 minus 3, which is 22 out of 52. So that's how you use the formula. However, if it's something that you can see conceptually, so like I can see the 52 cards, maybe you don't have to use the formula. Okay. For the next one, you're talking about employees. It says 9 years or less. How many of them have worked that long? So 100 are between 0 and 4. 59 are 5 to 9, so I add those together. Easy enough. All right. Independent events. If I want to know probability of A and B happening, I multiply the probability of A times the probability of B. I made a little note there that and means multiply, or means add. So in some of the problems before, we said or, and that's why we were adding. Now we're going to be talking about some probability that says and. Okay. If we have a random number generator and it's selecting 3 integers from 1 to 5, what is the probability that all 3 numbers are less than or equal to 5? Okay, so that means that there are 5 numbers to choose from out of the 20. I'm going to go ahead and reduce that. You'll see why in just a second. And then I think about, I'm going to do that 3 times because it's selecting 3 integers. So my probability is 1/4 the first time, 1/4 the second time, and 1/4 the third time because all the numbers could spit out again and again and again. For a probability of 1/64. Okay. If it was without replacement, so what that means is like whatever number you did the first time, you didn't get that same one the second time, you would then have to be thinking about 4 out of 19 and 3 out of 18 because you're taking a number away every time. Okay? I'm not multiplying that, but that's how it would look if you did not replace. But it does not say that that's what we're doing, so it's 1/64. You can also do a complement, and what that means, so if you had a classroom full of sophomores and juniors, and say no other grades, just sophomores and juniors, if say in this case, let's say 70% of the class is sophomores, well, what percent would have to be juniors? Well, 100% is 1 minus 0.7, which is 70%, is 0.3, because the two together have to add up to be 100% or the number 1. Okay. The most common spot to use this with is whenever you have probability that says at least. So 1 out of every 10 computers is faulty. What are the odds that in a shipment of 50, at least 1 is faulty? So if we know that at least 1 is faulty, we're going to find, to make this easier on ourselves, we're going to find the probability of all computers are good. Okay? And we're going to subtract that from 1, because if they're not all good, well, then at least one of them is bad, right? So probability of all good will be, well, probability of good in general is 9/10, because if 1/10 is faulty, 9/10 is all good. But we want that to happen 50 times. So that's pretty large, and you will definitely need Desmos for that one. But what Desmos tells us when we type that in is that it is approximately 0.99484, blah, blah, blah. There's some others. But that's about a 99% or 99.4% chance that at least one of them is going to be faulty. So that will help you on some of your problems. This is a common one in college statistics. So keep these notes for future reference.